Hi everyone, welcome to the first MIDAS expert webinar in Australia. My name is Yuk Ho Gui, Associate Director, Bridge Structures from AECOM Melbourne office. First of all, I would like to thank MIDAS for inviting me to present in this webinar. Let me briefly introduce myself and my company. I have 16 years of experience in bridge engineering. I design bridges in projects such as Go-Between Bridge in Brisbane, which is an in-situ balanced cantilever bridge with 117-meter main span, South Road Superway in Adelaide, a 2.8-kilometer long precast segmental viaduct, Omega Bridge in Gerringong Upgrade Project, a 7-span continuous incrementally launched concrete box girder bridge, Northwest Rail Link in Sydney, a 4-kilometer long precast segmental rail viaduct, a composite box girder bridge in Darlington Upgrade Project in Adelaide, which is the first composite box girder bridge built in Australia using SPMT. Currently, I'm working on proof engineering of Westgate Tunnel project in Melbourne. AECOM is a multidisciplinary engineering firm with business in more than 150 countries. Globally, AECOM has approximately 87,000 staff, 3,000 across Australia, and about 700 in Melbourne. AECOM is publicly listed on the New York Stock Exchange. We reported $20.2 billion of revenue for the 2018 financial year. AECOM is ranked number 1 in transportation and general building in Engineering News Records 2019 top 500 design firms. We are ranked 157 on the Fortune 500. AECOM is named one of the Fortune magazine's World's Most Admired Companies for the 5th consecutive year. This animation illustrates the construction sequence of an incrementally launched bridge. Incremental launching is a special construction method of building a bridge to overcome access problems or minimize disruption at ground level. Incrementally launched prestressed concrete bridges are built in segments in a casting bed. Finished segments are pushed out of the casting bed to leave space for the construction of subsequent segments. Special knowledge and high degree of temporary works integration are required in order to successfully design an incrementally launched bridge. Most of the superstructure construction activities are carried out at the casting bed area. Bridge barrier, bridge lighting, and drainage can be installed prior to launching. This technique is generally used for bridge spanning less than 60 meters. There are 2 distinctive stages to analyze, namely launching stage and in-service stage, and there are also 2 distinctive groups of prestress to accommodate the actions from each of these stages. Today's webinar will cover the following key aspects of designing a prestressed concrete incrementally launched bridge superstructure, which include design of launch geometry, temporary works, how they are incorporated in a MIDAS model, and what output can be obtained from MIDAS analysis. Design consideration of a launch bridge superstructure cross-section, modeling of a launch bridge in MIDAS, analysis of launching stages, analysis of in-service transient effects, section capacity check to AS5100, and permanent load deflection of bridge deck. If you have any question about this presentation, you can type your question in the question pane in your screen or wait until the question and answer section after my presentation. Launch geometry design is a key component of incrementally launched bridge design. It is therefore important to evaluate and verify the design of launch geometry. The launch geometry can either be designed by hand calculation or by CAD. In CAD, the center and radius of the launch geometry can be quickly obtained by drawing a sphere, passing through 3 control points along the road alignment. But to evaluate the launch geometry in CAD is a labor-intensive process, and the whole process needs to be repeated in order to incorporate changes in road alignment or abutment location. In contrast, a simple hand calculation method written in spreadsheet format can easily keep up with changes to road alignment. In most projects, the road alignment is not frozen until the very final design stage. Therefore, the most efficient way to design the launch geometry would be by hand calculation, followed by CAD verification once the road alignment is finalized. The design launch geometry of a curved bridge is a circular arc about an axis inclined in 3-dimensional space. Cross-sections are radial to the axis of rotation. Only one cross-section along the launch geometry is vertical, and the cross-fall of the bridge deck constantly varies. The projection of design launch geometry on vertical and horizontal planes is elliptical. In contrast, the road alignment is designed using independent circular or parabolic curves in vertical and horizontal planes. That's why the launch geometry seldom matches the intended road alignment. The derived launch geometry will be different to the road alignment in terms of coordinates, level, crossfall, and bearing angle at supports. Evaluation of these aspects of the launch geometry is necessary in order to understand how well the launch geometry approximates the road alignment. To define a launch geometry, we need to determine the center of launch geometry, radius of the launch geometry, bearing angle of the vertical radial section, and the inclination of the axis of rotation. These parameters can be calculated by using the coordinates and level of 2 abutments and their midpoints along the road geometry. The launch geometry design is summarized in 3 steps. Step 1 is to calculate the radius of launch geometry. With reference to this diagram, the circular arc is the launch geometry passing through point A, point B, and M selected from the road alignment. Using the coordinates and level of point A, B, and M, we can determine vectors AB, vectors AM, and vectors MB. The lengths of the sides of triangle AMB are equal to the magnitude of these vectors. By property of the vector cross product, then we get magnitude of vector AB cross vector AM equals to magnitude of vector AB times magnitude of vector AM times sine angle BAM. And if we rearrange sine angle BAM to be the subject, then we get the first equation. By the sine rule, the radius of the circle passing through points A, M, and B is given by magnitude of vector MB divided by sine angle BAM equals to 2r, where r is the radius of this circular arc. And by making r as the subject, then we get the second equation. By substituting sine angle BAM from the first equation to the second equation, then we get this expression for r, which equals to the product of the length of 3 sides of triangle AMB divided by 2 times the cross product of vector AB and vector AM. Step 2 is to calculate the coordinate of the center of the launch geometry, which is point C. First, we calculate the unit vector normal to the plane of launch geometry, this unit vector n, which is given by the cross product of vector AB and vector AM. And then when we consider triangle ACD, the length of CD, which is the magnitude of vector CD, is given by the square root of R squared minus the square of magnitude of vector AM divided by 2. The direction of vector CD is obtained by the cross product of vector N and vector AM. And by making this one as a unit vector and times the magnitude of this vector, then we get vector CD from this expression. Coordinates of the center point C can be obtained by vector OC, which is equal to vector OD minus vector CD. Then step 3 is to determine the bearing angle of the vertical radial section, the phi angle, and the inclination of the axis of rotation, which is theta. Suppose vector R, which is numerically equal to vector N, equals to R1I plus R2J plus R3K. The bearing angle of the vertical radial section phi is given by 180 degrees plus arctangent of R1 divided by R2. And the inclination of the axis to vertical, theta, equals to arc cosine R3. Along the launch geometry, the convenient way to describe the position of a selected point X is by the angle swept by the radius R from abutment A in the plane of the launch geometry, which is angle beta as shown in this figure. Consider vector Cx, which equals to Cx1i plus Cx2j plus Cx3k, and vector Ca, which equals to Ca1i plus Ca2j plus Ca3k. Cx1, Cx2, and Cx3 are the unknowns, which require the solution of 3 simultaneous equations. The first equation is to consider the dot product of vector Cx and vector R, because they are perpendicular, so their dot product is 0. And second equation is to consider the dot product of vector Cx and vector Ca. They have the magnitude of R, and the angle between this vector is beta, so that their dot product is R squared times cosine beta. The third equation is to consider the magnitude of vector Cx, which is equal to R. After calculating Cx1, Cx2, and Cx3, the coordinates of point X can be obtained by vector Ox, which equals to vector OC plus vector Cx. The shape of the bridge deck after launching can be considered as an extrusion of the radial cross-section about the axis of rotation. The trajectory of each point of a cross-section after launching is also a circular arc. Each point of a cross-section has its own radius and center, but share the same axis of rotation. The coordinates and level of any point in a cross-section along the bridge can be calculated using this method. After that, the design launch geometry will be compared with the design road geometry to see how well the road geometry is approximated. Coordinates, level, crossflow, and bearing angle at supports are the parameters to be compared. If the approximation is not good enough, the designer may need to consider varying the web height or cantilever length to improve the approximation. Using this method, the coordinates and level of points for the model can be calculated. The points are spaced nominally 1 meter for the launching stage analysis, and with additional points to capture segment joints and change in cross-section. The calculated coordinates and level can be easily imported to a MIDAS model using MCT command shell. There are a number of temporary works to be incorporated in a launch bridge design, and I will go through these one by one. Casting bed is the place where concrete segments are cast and launching tendons are tensioned. It consists of a couple of spine beams on a rigid foundation and a steel outer form supported on a separate foundation, which can be lowered for demolding. During launching, leading segments are cantilevered until they reach the next pier. Launch nose is attached in front of the first segment to reduce the cantilever bending moment in concrete segment. Usually the length of a launch nose is about 70% of the maximum launching span. Depth of the concrete box is dictated by the maximum launching span. Typical span length suitable for launching is between 30 to 60 meters. If the span is too long, then the superstructure will become too deep and uneconomical. In this case, temporary tower can be used to reduce the span length during launching. Launch jack and braking saddle are installed at the abutment in front of the casting bed. They utilize friction to move and stop the superstructure during launching. At the start or end of launching stage, the available friction is not enough for launching. A separate pulling system is required. For example, a pulling frame is attached to the end of the bridge for this purpose. Temporary bearing support the bridge during launching. They are located underneath the webs. These bearings can be purely temporary or be converted to permanent bearings afterwards. Launch pads are inserted between the bridge superstructure and temporary bearings. There is a sliding surface between the launch pad and temporary bearing to facilitate launching. On top of piers and abutments, side guides are attached at the top of the pier to provide lateral restraint during launching. Table form is to form the bottom face of top flange. This form is launched together with a segment from the casting bed and is pulled back to the casting bed after the bottom flange of the next segment is cast. Some contractor may prefer using a precast concrete panel as a permanent form so that table form is no longer required. This table summarizes the integration of temporary works to a MIDAS model. In the model, casting bed stiffness is represented by a series of vertical springs. Spring reaction is the load on the casting bed spine beams. Launch nose is modeled in MIDAS as beam element. Typically, a launch nose consists of a couple of parallel I-beams. In order not to overcomplicate the MIDAS model, these beams are modeled as a single combined beam. After the launching stage analysis, bending moment and shear force envelopes of the launch nose can be obtained from MIDAS. Temporary tower is modeled as a spring to account for its stiffness. Design actions of this tower are derived from spring reactions. Launch jack and braking saddle are not modeled. Available friction for launching is calculated using the launch abutment reaction. Pulling frame and table form are considered as a load only. Design of temporary bearing is based on pier load from MIDAS analysis. Side guides are modeled at lateral restraint at piers and abutments. The restraint force on side guide is based on pier reaction, crossfall of soffit, and lateral transient loads. There are a number of features in a cross-section of a launch box girder. I'm going to introduce and explain the function of these features. In most cases, the box section is cast in two poles with a construction joint located at top of webs. Very often, the bottom surface of the top flange is formed by a table form, which is launched together with the finished segment. It will be rolled back to the casting bed for casting of next segment. For this reason, a continuous path in the cross-section is required at the bottom flange. This means if local thickening of bottom flange at segment joint is required to accommodate pre-stressing anchors, and such thickening is required at the table form path, this thickening needs to be maintained over the entire length of the bridge. Also, if internal tendons are used for continuity pre-stress, blisters for pre-stressing anchorage need to miss the path of the table form. Soffit of bottom flange is usually provided with a nominal crossfall of 1% to ensure the bridge superstructure always lean against one side during launching. During launching, the bridge superstructure is supported by temporary bearing below the webs. As the width of temporary bearings is significantly more than web thickness, center of temporary bearings is always eccentric to center of web. Such eccentricity will create more adverse local bending and shear at bottom flange. To alleviate such effects, web is thickened at the bottom to reduce bearing eccentricity. Flanges can be quite congested with tendon ducts and anchorages. They need to be wide enough to accommodate all tendons. In a MIDAS model, the cross-section is input as a PSC section. By activating additional cross-section control points, the above-mentioned features can be captured in a MIDAS model. Most people use MIDAS graphical interface to set up an analysis model. Launching stage analysis require a lot of input for staging and grouping. To streamline the process, MIDAS has developed the ILM wizard for generating the bridge model, including tendons and staging. It is a convenient tool if the bridge arrangement suits the template of the wizard. However, if the wizard does not suit your bridge, you can use the text input feature of MIDAS to set up your model. To do this, you need to understand the required input to set up a launch bridge model. The text can be prepared using Microsoft Excel. If you are good at VBA, then a lot of tedious input can be generated by using a customized macro. The Excel input can be copied to MCT command shell in MIDAS for import. MIDAS text input feature allows text to be imported by parts. You can make sure the first part of input is correct before proceeding to the next. In fact, I like the text input feature of MIDAS, and most of my MIDAS models were set up using text. Staging is the most tedious part to input. I'm going to demonstrate how stage input is prepared in Excel. In my text file, I have defined the element, load, and boundary groups in a sequential order. Such numbering will enable me to obtain a pattern, which is capable to be generated by using formula in Excel. Staging is all about element, boundary, and load, and these are represented by a line or two in the input file. In this file, the middle part of it, which is from here to there, is the main input. The background inputs are on the right-hand side. The final input is on the left-hand side in blue color. This is the column eventually to be copied to MIDAS MCT command shell. In the input here, most of my inputs are actually like formulas, which refers to the background input here, so that the generation of the staging is mostly a copying and pasting exercise. Okay, in this section, we will go through a real-life example of a launch bridge. Here is a launch bridge model in MIDAS. The model consists of the bridge superstructure, the launch nodes, which is at the start of the model, and a series of supports which are activated or deactivated at different launching stages. In each launch stage, the bridge is nominally moved by a meter. So altogether, there are actually a lot of launching stages to analyze. This stage is at the beginning of the launch. This group of supports represent the casting bed. Compression-only elastic links are used at the casting bed and the launch nodes so that the structure can get lifted up if required. In MIDAS, the effect of launching is simulated by moving the support backwards rather than moving the superstructure forward. Just before launching prestress is activated. Okay, so this one is the load from the table form. As you can see, the table form load moves with the segment during launching. And after the second segment is activated, then the table form loading will be moved to the next segment. This cycle repeats until the end of the launching stage. Piers and abutments are represented by discrete supports along the bridge. This is close to the end of the launching stage. After the bridge deck is launched to the final position, beam elements representing the launch nodes are deactivated and continuity prestress is applied at this stage. The purposes of launching stage analysis are to ensure the stresses in the superstructure during launching comply with the appropriate requirements. Secondly is to evaluate the load during launching for the design of launching nodes, temporary bearings, temporary pier, launching abutments, and casting bed. And thirdly is to calculate the cumulative shortening of bridge deck due to prestress, creep, and shrinkage during construction. This is the bending moment envelope of the bridge superstructure from MIDAS analysis. While this is the output for a particular substructure arrangement, launching stage analysis of other bridges should give similar pattern. The peak sagging moment of the entire bridge appears at the leading segments. This happens when the leading segment spans across the maximum launch span, with the leading end of the first segment almost reaches a pier. Because the launch nose is light, cantilever moment of the launch nose offset only a small proportion of the sagging moment due to concrete weight. The peak hogging moment of the entire bridge also appears at the leading segments. This happens when the launch nose cantilevers at the maximum span, just before the tip of the launch nose reaching the next pier. Sagging and hogging moment of intermediate spans are quite uniform. This is because each cross-section alternates between a mid-span section and a support section. This diagram shows two distinctive magnitude of moment, with the magnitude of the second part being lower. This means that the pier of the second half of this bridge is more closely spaced. There is another peak towards the trailing end of the bridge. This happens when the trailing end of the bridge just leaves the casting bed and becomes a cantilever. There is one potential critical stage hidden inside this envelope. It happens when a segment is launched with some of the tendons in the flange stressed. Typically, tendons in flanges are 2 or 3 segments long. The tendons are staggered so that only half or a third of them are stressed at each launching stage. I will explain the tendon arrangement further later. The action on the superstructure is less, but the load effects needs to be checked with fewer tendons. MIDAS stage analysis does not include the transient effect at each stage. To analyze the total effects on the bridge stack during launching, we can identify critical stages from the moment envelope by comparing the result of each individual stage with the result at max mean stage. Then we can save the critical stages as separate models and apply construction life load, wind, thermal effects, and construction tolerance to the saved models. Arrangement of launching pre-stress can be determined according to the total action during launching. This plan shows the launching pre-stress arrangement of top and bottom flanges in the first 2 segments. Tendons for the launching can be lapped or coupled at segment joints. Tendons in this arrangement are lapped at segment joints. The blue tendons are the tendons stressed after casting of the first segment, and the green tendons are the tendons which are stressed after casting of the second segment. These tendons are 2 segments long. Tendons are terminated with a pocket at the leading end for fixing of wedges of strands. For coupling option, tendons are coupled at segment joints using proprietary couplers. When tendons are coupled, the strands are embedded inside flanges. It does not allow easy replacement if a strand breaks during stressing. As a result, strands are stressed to a smaller force at about 70% of breaking load. Pre-installed strand in this option will also interfere with reinforcement fixing of the subsequent segment. In contrast, lapping allows tendons to be installed just before stressing. This allows strands to be replaced if they break so that they can be stressed up to 80% of breaking load. However, lapping will require longer tendons and lead to more congested flanges. There are more anchorages in the lapped option, so that additional anti-bursting, spalling, and trailing reinforcement is needed. From my past experience, such reinforcement accounts for about 5% of total reinforcement tonnage. Moment and shear envelope can be obtained from MIDAS for the design of launch nose. As I mentioned before, The launch nose consists of a pair of parallel I-beams, and it is modeled as a single combined I-beam in MIDAS. So these envelopes give the total action of 2 I-beams. The temporary works designer will need to determine the appropriate share of the load to each beam to account for torsion and construction tolerance. MIDAS has a very useful feature called reaction position table. Since launching stage analysis is simulated by moving support backwards, the same pier is represented by different nodes at different stages. Reaction position table is to correlate the node number and stages with each pier or abutment to facilitate the output of support reactions. During launching, concrete segments become shorter due to elastic shortening at transfer of prestress and subsequent creep and shrinkage. If uncorrected, the diaphragm of the superstructure will not align with piers and abutment. As a result, the cumulative shortening of segments obtained from launch stage analysis needs to be compensated during casting. Such information can be easily obtained from MIDAS. After the launching stage analysis, in-service stage analysis is carried out to evaluate the transient effect as well as the load during bearing replacement. SM1600 live loads are predefined in MIDAS for influence line analysis. If the box girder section is defined as a PSC section, temperature profile for differential temperature can be defined directly as beam section temperature loading. Note that in the temperature profile defined in AS5100 Part 2, the temperature of the top flange is non-uniform. Weighted average temperature of top flange needs to be manually calculated to capture such variation. To design a prestressed concrete bridge, we typically need to know the moment envelope, shear envelope, and torsion envelope, and their coexisting effects. Design envelopes and coexisting actions can be conveniently obtained from MIDAS. Continuity prestress is provided according to actions due to transient effects. Continuity prestress can be provided as internal tendons within web or external tendons inside the box. Since there is no tendon ducts inside the webs, external tendons can simplify segment construction, and they are easy to install. A single external tendon can be up to 300 long for 2-end stressing. This is much longer than 150 meters for internal tendon because of less immediate prestress loss. However, internal tendons are typically more efficient because of larger eccentricity, higher tendon strength at ultimate, and more efficient tendon profile to minimize secondary prestress moment. The hardware for internal tendons is cheaper, and there is no need to worry about future tendon replacement. Usually, a contractor needs to understand the arrangement of these two options in order to work out the actual cost difference. Continuity tendons are profiled according to the actions due to transient effects. Internal tendons should be at least 150 mm clear of soffit of bottom flange. This is because the bridge is launched without continuity prestress. High bearing stress from temporary bearing may damage empty tendon ducts if they are positioned too close to the bearings. If the bridge belongs to exposure class B2, C1, C2, or U, concrete at tendon level must under compression under a SLS combination of permanent effect plus 25 or 50% of transient effects. This will dictate the required quantity of continuity prestress. Additional longitudinal reinforcement is then added to satisfy the steel stress increment limit at SLS and to improve ULS bending moment capacity. If the bridge belongs to a less severe exposure class, I would provide maximum possible passive reinforcement in flanges without making the flange over-congested, and then the shortfall to stress increment limit and ULS bending capacity will be made up using continuity tendon. Transverse reinforcement is provided to ensure adequate quantity is provided for ULS shear, torsion, and local bending. It is worth noting that Big Rose BTN 025 requires shear and torsion design of pre-stressed concrete beam to follow 2004 version of AS5100 Part 5 rather than the current version of AS5100. Quantity of local bending reinforcement is obtained from a separate transverse analysis, which is not covered in this webinar. ULS longitudinal shear at web flange interface and construction joints should also be checked. MIDAS can output permanent load deflection at both short-term and long-term. Self-weight of bridge deck will produce sag deflections at midspan regions after launching. AS5100 Part 2, Clause 7.11 does not allow sag deflection under permanent loads. Vertical camber cannot be incorporated during segment casting. The only way to reduce sag deflection is by continuity pre-stress. However, it would be uneconomical to eliminate sag deflection solely by continuity pre-stress, especially for longer spans. The effect of net sag deflections should be assessed with respect to visual impact, required clearance underneath the bridge deck drainage, and additional servicing weight to restore the roll profile. If this is acceptable from an engineering perspective, it is advisable to seek a dispensation from the asset owner at an early design stage to avoid lengthy discussion at subsequent review stages. Today, I have introduced the concept of incremental launching, the geometry and structural design of a launch bridge, MIDAS modeling, and the output for temporary works and permanent works design. From my presentation, I hope you can understand the key design issues of a launch bridge and what MIDAS is capable of as a bridge analysis tool. This is the end of my presentation today. Thank you for listening. Feel free to ask if you have any questions. Okay, I've got a question from one of the audience. So it is not actually a technical question. He is asking whether it is possible to obtain a copy of the recording. And I believe MIDAS should have recorded this presentation, and they will later upload this presentation to YouTube, and you can ask MIDAS for the link. Okay, I've got a question here, which asks about the concrete stiffness. So I think the question is about like whether the short-term or long-term concrete stiffness is used in the model. So the answer is we have a, like in MIDAS, there is a time-dependent concrete property to be which can be defined like either using the inbuilt creep and shrinkage model or using a customized creep and shrinkage model. And if you use the customized model, then you will actually like for the creep, you need to define 32 curves, and each of them correspond to the age of concrete at the time of loading. So with these 22 curves, then MIDAS can pick the correct creep factor with respect to the age of concrete when you apply a particular load defined in the construction staging. Yeah, and then for shrinkage, I believe just one single curve is enough to define the time-dependent shrinkage. Okay, so another question here. is when calculating deflections, does MIDAS consider the cracked or uncracked stiffness of the concrete? Okay, so the answer is it depends on what you define in the model. If you define uncracked section, then it will give you the deflection based on uncracked stiffness. And yeah, if you define a cracked section, then of course it will give you a larger deflection because the I value is smaller. If you want to capture, like to make it very accurate and capture all these cracked property, then actually you need to work out the crack stiffness manually to start with, and then apply the stiffness modification factor in MIDAS. Yeah, because in MIDAS there is a function to activate this factor at a particular stage, so that when you know the concrete after a certain stage will become cracked, then you can start activate this reduction factor so that the I value is reduced. Okay, I've got another question. It's about how to brace the temporary intermediate columns. Okay, so I think like whether you need to brace it or not will be based on the outcome from your temporary works design. And if you find that the temporary pier is too slender, then you will need to apply some additional ties or brace, like so that the deflection of the pier will be, like temporary pier will be more controlled. And I think the same concept also applies to permanent piers. Yeah, because in some cases the permanent pier will be very slender, because for launch bridge design, one of the benefits is to overcome the access problem. So a lot of the launch bridge is actually across a deep valley. So some of the piers will become very slender, and in this case, even the permanent piers will require some bracing. Okay, I've got another question here. The question asks, are the lateral restraints to take care of wind loads additional to uncertainty loads during launching? Yeah, so I think this lateral restraint refer to the side guides, which are attached to the top of the piers and abutments. And yes, they are the only device which prevent the bridge from sliding sideways. So they have to take basically all the lateral effects, yeah, from the bridge. Okay, so there is a follow-up question with the cracked property. So the question is, so it won't calculate whether the concrete is cracked or uncracked and then calculate the deflection. Yeah, so I think I don't think MIDAS is so automatic with respect to this. So I think in terms of the appropriate section property for deflection calculation, you still need to use your judgment to work out what is the appropriate value of stiffness for this calculation. Okay, a question is about the lateral load on piers during launching. Yeah, so what kind of load will happen during launching? So obviously wind is one of them, and then and also due to the crossfall of the bottom flange. Yeah, because in my webinar I mentioned that the bottom flange will have a 1% crossfall to ensure the bridge always lean against one side. So this 1% will have some effect on the lateral load. So it will be just simply work out the component of the weight along this crossfall direction. Yeah, and I think if the bridge is curved, yeah, because for the launching jack, it is always pushing towards the tangential to the launch geometry. So if the bridge is curved, so for the piers further away from the launch abutment, then this launch force will have a component of force transfers to those piers. So for those piers, then there will be some additional force to consider. during launching. But I believe like these site guides are usually designed by the specialist subcontractor who do the launching, so they would normally take care of all these loadings. Okay. Yep. Another question is for this bridge, how many MIDAS models were created and used for the design? Okay. So so for the main analysis, the launching the in-service stage, like one model is enough. But then during launching, you need to identify the critical stages for basically for each segment or each pre-stress type, so that you can apply the transient effect to those critical stages. So so the short answer is like there is no fixed answer. It depends on the actual geometry and your proposed pre-stress design. Okay, another question is about what are the geometry, horizontal alignment constraint, or the radius limitation. Okay, so like the aim of the launch geometry design is to obtain the best approximation of the road geometry by launching. So like we have to like understand that the launch geometry will never match the road geometry. So the purpose of this the design exercise is to make sure the difference is as small as possible, and those difference will be considered as construction tolerance. And if those differences within the tolerance specified in the specification, then we can accept this design launch geometry is good enough to approximate the original road design. Okay, another question is the coupler used for continuous tendon? If it is, how you model it in MIDAS? Okay, so the question here is basically we seldom use coupler for continuous tendon. The reason is like just think about how the tendon is coupled, right? So when you have an internal okay, so perhaps this question I will separate between external and internal tendon. So if it is internal tendon, then the answer is you seldom couple it, because like when you stress the internal tendon, you will need to have the entire structure finished. So which means there is no way you can have access to the coupler to couple the tendon. So for the if it is an internal tendon, then those tendons are usually left at the blister. And for the blister design, then is to be very careful about like how the coupled tendons are how the left tendons are crisscrossing locally, and just to make sure the space is enough for the curvature, and also the anti-bursting reinforcement, and also consider the jack clearance. And if it is external tendon, it is actually possible to couple it. So for coupling of tendon, it can be modeled in MIDAS. So I think like what you actually need to do is to activate the first part of tendon in MIDAS, and then after that you activate the second part of the tendon as a separate tendon in MIDAS. Then from there you can model the coupling of tendons. Okay, so we have another question here. It asks like what age of concrete was set up for determining deflection or precamber for not allowing sag? Okay. So first thing is like we can't precamber a launch bridge. The reason is because all the segments are cast using a rigid casting bed, so that the shape of the segment cannot be altered to suit the precamber the precamber profile, right? So that like for launch bridge, all the segments will have the same geometries, no precamber can be applied. And then for the sag deflection, so like according to the code, it's basically anytime, like short-term and long-term, the bridge cannot have a permanent sag. So we just look at like either that both we look at both the short-term and long-term sag deflection, and whichever the worst will be the critical one to look at. Okay, a question here is to ask, how do you ensure there is enough weight for friction at the launching jack? Okay, so like first of all, the launching jack design is usually like a very specialized item provided by the launching subcontractor. So they will have the information about like what sort of friction coefficient it is for those systems. As a designer, what we need to provide them is to like tell them for the launch abutment, what is the variation of abutment reaction at each individual stage, and then from there, the launching subcontractor can determine at what stage they can use the launching jack, and at what other stage they need to use some additional system to pull the pull the bridge forward. And in some cases, the launch contractor may ask you to like whether you can lift up the bridge, like jack up the bridge a little bit more in order to create more friction due to the stiffness of the girder. Yeah, but I think like these are the case when the things become marginal, then the subcontractor want to get more from the from their launching jack system. Okay, and a question here is about how do you do summary of output data from analysis? Is result beam element useful in that case? Yes, yeah, there are actually two groups of output right, to be processed for this design. The first one is for the launching stage analysis. So basically, all the output is from the results table of the beam element forces. For the launching stage analysis, what I would do is to like look at the maximum minimum stage, which gives you the overall envelope of the most adverse action along the bridge. Then from there, you like yeah so I think at the same time, you also need to have some idea about what sort of pre-stress arrangement or how many types of pre-stress arrangement will be designed along the bridge. Then within each type, then you pick one point which is the most critical, and then from this point, then you can like from open another table with this element only, and look at the variation of the actions from the start to the beginning of the stage, and compare with the value to the max mean stage. From there, you can pinpoint which stage is critical, so that you can proceed further to do the transient to input the transient load for this particular stage. And then for the in-surface stage analysis, is basically to like look at this result table and also to look at the maximum minimum value item, so that you get the coexisting effect. Say when I pick the maximum moment envelope, then what will be the coexisting shear and torsion, etc., etc. So like all this, yeah, is from the beam element result table. Okay, now it is actually after 1 o'clock already, so I think this webinar needs to come to an end. And if you have any question or feedback, then you can email to MIDAS and we will answer from there. Thanks again for joining us today. Goodbye.